Consider the optimization problem of maximizing profit between creating tables and chairs. Each table gives you $40 of profit, and each chair gives you $25 of profit. Let's also say you have labor and material constraints. Let's say that tables and chairs both cost you 3 labor units, and you cannot exceed 240 labor units. Let's also say that tables and chairs cost 2 and 1 wood units respectively, and you cannot exceed 100 wood units of supply. We can plot both constraints on the Cartesian plane. In green, every point in the shaded region satisfies our labor constraint. In red, every point there satisfies our material constraint. Their intersection is the region we need to look at, where both constraints are met. Now consider plotting our profit function equal to sum z. Note that wherever this line intersects our region is a valid solution. When we try to maximize z, let's see how far we can go. It looks like the furthest we can go is z equals to 2300. Therefore, the maximum profit we can make is $2,300, where we make 20 tables and 60 chairs. Consider the optimization problem minimize ct of x subject to x being an element of our polytope, where our polytope is defined as the intersection of half-planes. If x star is an optimal solution to the problem, then x star is either an extreme point, a vertex of P, or lies on a face of optimal solutions. To prove this, suppose for the sake of contradiction that x star is in the interior of P. Then there exists some epsilon ball that's entirely contained in P. Now let's consider a new point in the ball which must also be contained in P. This point, when we plug it into our objective function, can be simplified as follows. Note that CTC is just each component squared, which is the same thing as the magnitude squared. Therefore, we can write the right-hand side as c squared magnitude over the magnitude of c. This simplifies to just the magnitude of c. Since epsilon over 2 times the magnitude of c is a positive constant, we know that this must be less than our original optimal solution. This is a contradiction, thus x star must be on the border of P. If x star is not a vertex itself, it must be the convex combination of vertices of P, say x1, x2, all the way to xt. Here, the vertices are x1 and x2. Then, x star is a weighted combination of the vertices with weights lambda. Now, observe the following algebraic manipulations. X star can be represented as the convex combination of vertices. And on the right, x star can be multiplied by a fancy form of 1. Rearranging and then multiplying gives the following. Since all the terms which are non-negative sum to 0, each individual term must equal 0. Therefore, CTXI must equal CTX, meaning xi, the vertices of the face, are equally as optimal. Here is the analogous 3D visualization. Since x star is on the boundary of our polytope, it must also lie on a face. This means that it can also be represented as a convex combination of the vertices. The same argument applies, and every point on the face must also be optimal. And the proof is complete. Either a vertex is optimal, or the entire face which the vertex lies on is optimal. Thank you for watching.